Today we're going to take a look at a couple more integrals that we can just solve using geometry before we really get into some really cool techniques for finding the value of integrals. So here we're looking at the integral from -1 to 3 of the absolute value of x. Well, we know what absolute value looks like, right? It's just a v-shaped function here, right? And if we're at -1 and we're over here at 3 and we're talking about this total area, then we can see that that's just two different triangles. And so we should be able to write this out as the area of the first triangle, 1/2 of the base, which extends from -1 to 0, so 1, times the height, which is, at -1, the absolute value of -1 is 1, so this distance here is 1. So 1/2 of 1 times 1. And then we'll just add that to the 1/2 of this base, which is 3, and this height, which is also 3. So we end up with 1/2 times 1 times 1, which is 1/2, plus 3 times 3 is 9, times 1/2 is 9/2, 1/2 and 9/2 is 10/2, which is just 5. So we don't actually have to know how to integrate absolute value. We just need to know and understand what this means. It means find this area between the function and the x-axis. Okay. This time we're going to be looking at the integral from -2 to 4 of 4 minus the absolute value of x. So hopefully you know what this function looks like. It's going to have a y-intercept of 4. So up here at 4. And then it just is going to be just like the absolute value function, except upside down. And so we're going to go from -2 to 4. Well, 4 will be over here, and -2 will be somewhere over here. We can see that this time, this area works out to be a trapezoid in blue here, plus a triangle that I'm shading there in black. And so for the blue one, it should be base 1. And if we were to evaluate this function at -2, the absolute value, -2 is 2, 4 minus 2 is 2, so this height here is 2. So our first base is going to be 2, and our second base is the height here in the middle. That height is 4, so 2 plus 4, and then average the bases, base 1 plus base 2 divided by 2, times the height, and that height is extending from -2 to 0, which is 2. And then we'll add to that the area in black of that triangle, which is 1/2 the base of 4, as we go from 0 to 4. And then the height is also 4 there. 4 times 4. Looks like we've got 6 over 2 is 3, times the 2 is 6. So we got 6 plus 1/2 of 16, which is 8, which gives us a value for this integral of 14. Once again, we don't need to be able to integrate absolute value. We just need to understand what the function looks like and be able to find the area underneath it. This time, we're going to look at something like an integral from -4 to 4 of the square root of 16 minus x squared. Now, hopefully, you know exactly what this function looks like. This is of the form y equals the square root of a squared minus x squared, or r squared minus x squared. And, this is just a semicircle that, if it was a full circle, would be centered at the origin that's lying right across the x-axis. So this is just going to go from -4 to 4. So really all we're looking at here is a semicircle, right, with a radius. I don't know why I wrote A before, but we'll call it A, which is the radius, which is just 4. So all this is asking you for is, what's the area of a semicircle with a radius of 4? Well, that ought to be 1/2 of pi times the radius, which is 4, squared. And so we just end up with 8 pi as the value of this integral. And if you look at square root of 16 minus x squared and you're not quite sure that that's a semicircle, you should be sure that's a semicircle, but if you're not, you can always write it as y equals root 16 minus x squared and then square both sides, giving you y squared equals 16 minus x squared. And if you add the x squared over, it looks like the nice standard form for a circle, x squared plus y squared equals 16. Since it started as a positive square root, we know it's the upper half of the semicircle. If it had been y equals negative square root of 16 minus x squared, then we know it'd be the bottom half of this semicircle. And so being able to do this is going to help us out a little bit with the next couple of problems here. Because we might look at this, 2 plus the square root of 4 minus x squared, and think it kind of seems like it should been a semicircle here, but we're not maybe exactly sure what it looks like. So let's start off with y equals 2 plus root 4 minus x squared, and just see what this thing looks like so we can kind of help ourselves ground it. So first thing I'll do is I'll subtract the 2. So y minus 2 equals root 4 minus x squared. And if I square both sides, we get y minus 2 squared equals 4 minus x squared. And adding the x squared over just gives me x squared plus y squared. Sorry, x squared plus y minus 2 squared is equal to 4. And so we should see that this is a circle that is centered at 0, 2. That has a radius of 2. So if I were to be drawing the full circle, it would look like this. But since I started with a positive square root out there, we know it's just going to be the upper portion of this semicircle. And if that was not a good looking semicircle, I've tried. Let's try that again. We'll pretend that's better. All we've got to do is find the area of that semicircle and everything underneath it. And so if I'm talking about everything underneath it, I'm talking about all the way down to the x-axis. So what I've really got is a semicircle plus, in blue here, a rectangle. So the semicircle part of it ought to be 1/2 pi times the radius squared, and our radius here was a radius of 2. And then we'll add to that the section in blue, which is a rectangle that has a width of 4 and a height of 2. So this area here is just, well, 2 squared is 4, divided by 2 is 2, 2 pi plus 8. And we'll look at one more. Now this one is almost exactly the same as the previous one, except that it's got the minus sign. So we've got the same graph here, right? We've got, here's 1, 2, but this time the semicircle looks like this. It's the bottom half of that circle instead of the top half. So this complicates things a little bit as we go from negative to 2 over here, because what we're actually looking for is not the area inside the semicircle, it's the area between the function and the x-axis. So it's actually what's outside of that semicircle. Now, in the last problem, we had a little rectangle here. Pretend that actually went through at the mark where I made it at 2. That's closer. We had that rectangle that had a width of 4, but we need to then subtract that semicircle to get the area underneath it. So we're looking at the rectangle minus the semicircle this time. And the rectangle is, again, 4 units wide by 2 units tall. And that semicircle is, again, 1/2 of pi times its radius of 2 squared. So now we've got 8 minus, and then 2 squared is 4 divided by 2 again is 2, 8 minus 2 pi. And you'll see that when we get to talking about some of the free response questions on the AP test, you won't necessarily need to find an integral of some equation that looks like this, although that is helpful. You will be given some graphs and be asked to deal with integrals of just graphs. And oftentimes in those graphs, you'll have semicircles. You have to take into account whether we're looking at a chunk of it that's above the x-axis and we're going below it, or some piece of it where the part that's the integral is the part outside of the semicircle. So just something to get used to working with as we move closer and closer towards the AP test. And that's going to be it for our integrals using geometry. Next time, we're going to kind of get into some proofs of what the fundamental theorem of calculus is, relating integrals and derivatives together. Then we'll be able to take all kinds of integrals after we do that.